Every atom in your body came from a star that exploded before our solar system formed. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all forged inside stellar furnaces billions of years ago. You were assembled by this universe, from this universe. The constants that allow atoms to exist and stars to burn sit at values so precise that shifting any one of them would produce a cosmos containing nothing at all. If this grips you, subscribe, because today we ask the question nobody warned you about. What if the universe is not the container you live inside, but a living system you are already part of, and the most unsettling evidence has been in plain sight all along? The rules that govern everything you have ever seen, touched, or thought about fit on a single page of mathematics. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force, 4 interactions. A handful of constants that set their strengths. Every star that has ever burned, every atom that has ever formed, every heartbeat that has ever occurred runs on these 4 forces and nothing else. You might expect a universe as varied and complex as ours to require elaborate machinery, thousands of special instructions, countless exceptions and overrides. Instead, it runs on equations compact enough to print on a shirt, governed by a parameter list shorter than a grocery list. And the extraordinary thing is not the simplicity. The extraordinary thing is that the settings appear to be calibrated with almost impossible precision to allow stars rather than empty gas, chemistry rather than dead elements, minds rather than void. Change any one of the fundamental constants by even a modest fraction, in several cases, by less than 1%, and you do not get a different kind of universe. You get no universe at all, not something unrecognizable. Just featureless, nothing, expanding in silence forever. Physicists call this the fine-tuning problem. It is one of the deepest unsolved puzzles in all of science, sitting at the boundary between what can be measured and what can be explained. The specific values of the fundamental constants appear exquisitely calibrated for complexity. Gravity must be strong enough to pull gas into stars, but weak enough on the atomic scale to allow stable atoms. The nuclear force must be strong enough to bind nuclei, but not so strong that all hydrogen fused in the first seconds after the Big Bang. The energy efficiency of nuclear fusion must sit in a precise range that allows stars to burn steadily for billions of years. The cosmological constant, the energy of empty space, must be small enough that the universe does not expand too fast for gravity to ever build structures. The density of matter in the early universe must have been balanced against the expansion rate to extraordinary precision. Each constant is individually constrained. Together, they form a network of mutual dependencies, all simultaneously satisfied in a way that produces atoms, chemistry, planets, and minds. The probability of this happening by chance, in the usual sense of the word, is not small. It is essentially 0. What makes this situation genuinely puzzling rather than merely curious is that physicists did not set these constants. They measured them. The constants are inputs to our equations, not outputs. No deeper theory derives their values. They appear, as far as current physics can determine, to be genuinely free parameters. They could have been different. The universe could have had a different gravitational constant, a different nuclear force, a different efficiency of fusion. As far as we know, nothing prevents it. And if the constants could have been different, then the fact that they are precisely the values that allow our existence is a fact that demands explanation. That explanation is not provided by any theory in the current inventory of science. The gap between the precision of the observation and the absence of any explanation is the problem. It is not going away. And it is the starting point for the most radical ideas in modern cosmology. The ratio of gravity to electromagnetism is one of the most striking numbers in physics. Gravity is weaker than electromagnetism by a factor of roughly 1 followed by 36 zeros. This immense disproportion is not an accident of the way forces are defined. It is a physical fact with profound consequences. On the scale of individual particles, gravity is essentially irrelevant. It is so weak that it contributes nothing to the forces that hold atoms together or drive chemical reactions. Electromagnetic forces dominate the microscopic world, holding electrons in orbit around nuclei, governing chemical bonds, determining the structure of everything from simple molecules to complex proteins. But gravity accumulates with mass. As you pile matter together, gravity grows. A planet has enough mass that gravity shapes its structure and holds its atmosphere. A star has enough mass that gravity compresses its core to temperatures and pressures where nuclear fusion ignites. Galaxies and galaxy clusters are held together by gravity acting across scales where electromagnetism is negligible. The specific ratio between the two forces determines the boundary between the microscopic world governed by electromagnetism and the macroscopic world governed by gravity. Change it, and you change stellar physics fundamentally. Make gravity stronger relative to electromagnetism, and stars burn 1,000,000 times faster, exhausting their fuel in thousands of years instead of billions, leaving no time for planets to form or chemistry to develop. Make gravity weaker, and the threshold for stellar ignition rises too high. Gas clouds never compress to fusion temperatures, and no star ever forms. The strong nuclear force has its own window. It binds protons and neutrons together inside atomic nuclei against the electromagnetic repulsion between positively charged protons. Its strength, relative to other forces, determines what elements can exist. If the strong force were about 2% weaker, the deuteron, a proton bound to a neutron, the first step in hydrogen fusion, would not be stable. Stellar fusion would not occur. The universe would be forever hydrogen. If the strong force were a few percent stronger, the diproton, two protons bound together, would be stable, and fusion in stars would run far too fast, consuming all available hydrogen almost immediately. The universe would run hot for a brief moment and then go permanently cold and dark. Both failure modes are total. Our strong force sits between them, not near the edge of the habitable range, but comfortably within it, allowing stable nuclei for the first 92 elements, allowing stellar fusion to proceed steadily for billions of years, allowing the buildup of chemical complexity that eventually produces everything. For the initial density of matter in the early universe, the precision required is at least 1 part in 10 to the 60th power. If the density had been fractionally higher relative to the expansion rate, gravity would have overcome expansion, and the universe would have recollapsed before a single star had time to form. If it had been fractionally lower, matter would have dispersed so rapidly that gravity could never have pulled it into structures. The universe began its existence balanced on a point so precise that writing the precision in standard notation requires more digits than most people have considered in their lifetimes. This is not a philosophical abstraction. It is a calculation based on the measured properties of the universe, a consequence of the equations of general relativity applied to the initial conditions. The universe started out extraordinarily ordered in a way that permits the very long, very structured history it has had, and we have no explanation for why. In the 1950s, Fred Hoyle sat down to work out the mathematics of carbon formation inside stars. Hoyle was one of the most brilliant and combative scientists of his era, a man who had spent years arguing against religious and mystical interpretations of cosmology, who coined the term Big Bang as a dismissive mockery of what he considered a naive theory. He was not looking for evidence of design. He was trying to solve a technical problem in nuclear astrophysics. The problem was this: carbon forms inside stellar cores when 3 helium nuclei collide and fuse into a single carbon nucleus. This process is called the triple alpha reaction, and it is what stands between a universe of hydrogen and helium and a universe with a periodic table. The trouble is that 3-body simultaneous collisions are extraordinarily unlikely, even inside the compressed, energetic interior of a star where collisions happen constantly. By straightforward probability, the The triple alpha reaction should be far too slow to produce the carbon abundance we observe. The calculation and the reality were completely at odds. We exist. We are made of carbon. The universe contains vast amounts of carbon-based chemistry. The naive calculation says this should not be possible. Hoyle resolved this through a deduction that many physicists still find startling. For carbon to form efficiently, the carbon nucleus must have a quantum mechanical resonance, a specific energy state, at a very precise energy level. This resonance would act as a funnel for the triple alpha reaction, dramatically increasing the probability that the collision results in a stable carbon nucleus rather than an immediate disintegration. Without the resonance, the reaction is negligible. With it, carbon accumulates efficiently inside stellar cores over millions of years, eventually being scattered into space when the stars die, seeding the interstellar medium with the building block of chemistry. Hoyle calculated exactly what the resonance energy would need to be. He did this using no information about atomic physics. He used one observation: that complex chemistry is possible, that carbon exists in abundance, that we are here. He published the prediction. Physicists in the laboratory measured the relevant energy state of the carbon nucleus. The resonance was exactly where Hoyle's argument from our existence required it to be. Not approximately, exactly. A specific quantum property of the carbon atom was precisely calibrated to make carbon production efficient in stellar cores. Nothing in the theory of atomic nuclei at the time predicted this resonance. Nothing predicted it would be at that specific energy. Hoyle calculated it by backward reasoning from the fact of our existence, and the universe had done exactly what was required. Hoyle spent years troubled by this. He wrote that the universe appeared to have been arranged by a superintelligence. He did not mean this as theology. He was one of the least religious scientists of his generation. He meant it as a description of improbability. The carbon resonance is not like a coincidence in the usual sense of the word. It is not like a remarkable card draw or an unexpected meeting. It is a precisely calibrated quantum mechanical property of the carbon nucleus that sits at a value derivable only from the observation that chemistry is possible. Remove it, and the universe contains no carbon, no organic molecules, nothing from which life as we know it could form. It is there, and nobody has explained, within any physical theory, why it has the specific value it has. A physicist named Lee Smolin looked at the fine-tuning problem and noticed something nobody else had articulated in quite the same way. The problem looked familiar, not from physics, from biology. Before Darwin, biologists faced a problem structurally similar to fine-tuning. Organisms appeared exquisitely adapted to their environments. The eye was perfectly designed for vision, the wing for flight, the gill for underwater breathing. Every structure seemed calibrated for its function with a precision that seemed to require intentional design. The only explanation that made sense to most people was that an intelligence had designed each organism for its purpose. Darwin showed this was wrong. Adaptation can emerge from a blind, undirected process. Random, heritable variation acted on by differential reproductive success, repeated over many generations. No intelligence required, no intention required, just variation, differential reproduction, and time. Smolin asked, could the same logic apply to universes? Could the constants be what they are not because they were designed or chosen at random, but because universes with these constants produce more offspring than universes with different constants? And could black holes be the mechanism by which universes reproduce? The proposal is called cosmological natural selection, and it works as follows. When a massive star collapses into a black hole, the interior reaches extreme densities where general relativity's equations break down. In several approaches to quantum gravity, particularly loop quantum gravity, the collapse does not end in a singularity, but in a bounce. The matter is compressed to the maximum density that quantum spacetime can accommodate and then rebounds outward, creating a new region of spacetime, expanding away from the collapse point. This new region is causally disconnected from the original universe. It expands into its own history. It has its own timeline. From the perspective of anything inside it, it would look exactly like a new universe beginning from a hot, dense initial state, a new Big Bang. If this is correct, the constants of the new universe are not identical to the parents. They are inherited with small, random variations. Most variations are harmful. They produce universes with fewer stars, fewer black holes, less complex structure. But occasional variations increase black hole production. Universes with such variations leave more offspring. Their constants propagate through the population of universes. Over many generations, the multiverse, the collection of all universes, comes to be dominated by those with constants near optimal for black hole production. Our universe, as one member of this population, should have constants near that optimum. The critical and beautiful connection is that the constants that maximize black hole production also maximize everything else we observe. Black holes require massive stars. Massive stars require the nuclear force to be at its specific value, strong enough for stellar fusion, weak enough not to consume all hydrogen immediately. That same nuclear force, at that same value, enables the stellar nucleosynthesis of heavy elements. Heavy elements enable chemistry. Chemistry enables biology. A universe optimized through blind reproductive selection for black holes ends up, as a necessary side effect of that optimization, being compatible with atoms, molecules, planets, and minds. You are not the target of the selection. You are the collateral complexity, the byproduct of the universe's long reproductive history. There is a place in our galaxy where something is happening that our physics cannot describe. This is a technical statement, not a dramatic one. At the center of every black hole, according to the equations of general relativity, there is a singularity, a point where matter is compressed to infinite density, where space-time curvature is infinite, where every physical quantity that matters goes to infinity, and the equations stop producing meaningful results. Physicists do not believe singularities actually exist in nature. When a theory produces infinities in physical quantities, it means the theory has exceeded its range of validity. The singularity is not a feature of reality. It is a confession by the theory that it has reached the limit of what it can describe. For decades, physicists assumed the singularity would eventually be resolved by a better theory, a quantum theory of gravity, unifying general relativity with quantum mechanics. The unified theory would replace the singularity with something finite and describable, presumably something extreme, but not fundamentally mysterious. This was the working assumption. The singularity was a temporary placeholder, marking the location of something real that a better theory would eventually explain. The specific replacement that several serious approaches to quantum gravity suggest is extraordinary. In loop quantum gravity, one of the two leading candidates for a quantum theory of gravity, space and time are not continuous at the smallest scales. They have a minimum unit of size, called the Planck length, below which the concept of distance loses meaning. When matter is compressed toward a black hole singularity, it approaches the Planck density, the maximum density the quantum structure of space-time can support. At that point, the quantum pressure of discrete space-time pushes back. The collapse does not continue to a singularity. It bounces. The matter reaches maximum compression and then begins to expand outward. The bounce does not send matter back into our universe. The interior of a black hole is causally disconnected from its exterior. Nothing can travel from inside the event horizon back out by the definition of what an event horizon is. The bounce creates a new region of space-time, expanding outward from the point of maximum compression, completely disconnected from our own, a new space-time, a new cosmic history. From the perspective of anything that might exist inside this new region, it would look exactly like the early universe looks to us, an initial state of extreme heat and density, expanding and cooling, with all the subsequent stages of structure formation, star formation, and everything that follows still in the future. The event horizon is not a physical surface. You cannot stand on it or touch it. It is a geometric boundary in space-time, the sphere within which the curvature of space-time is so extreme that all possible trajectories lead inward. An observer falling through the event horizon of a large black hole would notice nothing special at the moment of crossing. No alarm bells, no physical sensation. The horizon is not a place where physics changes dramatically from one side to the other. It is simply the boundary beyond which communication with the outside universe becomes forever impossible. Once inside, the future leads, inevitably, toward the extreme densities at the center, and, if loop quantum gravity is right, toward a bounce into somewhere new. Our galaxy contains roughly 100 million black holes. Most of them are stellar mass black holes, the collapsed remnants of massive stars that exploded in supernovae billions of years ago. Their masses range from a few times the mass of our own star to perhaps 50 or 60 times that. They drift through the galaxy in silence, interacting with their surroundings only through gravity, invisible except when they pull in nearby matter, and that matter glows as it falls in. There are also neutron stars in similar numbers, the remnants of stars not quite massive enough to form black holes, and at the center of the galaxy sits a supermassive black hole with a mass roughly 4 million times that of our own star. The galaxy is populated with black holes at every scale. The observable universe contains somewhere between 100 billion and 2 trillion galaxies. Each galaxy has its own population of stellar mass black holes, its own history of supernovae and stellar deaths, its own central supermassive black hole. The total number of black holes in the observable universe is a number that requires scientific notation to express, something like 10 to the 18th power, possibly larger. Each one of those objects is, if Smolin's cosmological natural selection is correct, a potential universe birth event. The collapse of each one either ended in a singularity or bounced into a new universe. If even a fraction of them bounced, the number of universes generated by our single observable universe is incomprehensibly large. Now extend this across time. The observable universe has been forming black holes since the first massive stars died roughly 100 million years after the Big Bang. That was over 13 billion years ago. Black holes have been forming continuously since then. The rate has varied. It was higher when the star formation rate was higher, in the first few billion years, and has declined as the universe has aged and its gas supply has been depleted by successive generations of star formation. But the total inventory accumulated over 13 billion years is enormous. And extend further. If each new universe generated inside a black hole goes on to form its own stars, its own black holes, its own reproductive events, the multiverse implied by cosmological natural selection is more than large. It is recursively vast. Universes generating universes in a branching structure that has been running for however long the whole process has been operating, which might be far longer than our own universe's 14 billion years. Our universe is one node in a genealogical tree of cosmic reproduction that extends back to some original ancestor universe and forward to all the offspring being generated right now. Inside every black hole currently collapsing in every galaxy in the observable sky. This scale changes the framing of the fine-tuning problem. It is no longer, why does our universe have constants compatible with complexity? It becomes, given a population of universes that has been evolving by reproductive selection for an enormous span of time, is it surprising that we find ourselves in one near optimal for black hole production? The answer, by the logic of natural selection, is no. We would expect exactly this. The constants that seem improbably tuned for complexity are not a coincidence and not a design. They are the expected outcome of the process. They are what winning looks like in a competition that has been running longer than we can comprehend. Stars are the universe's metabolic engines. They take in hydrogen, the lightest, simplest element, produced in vast quantities in the Big Bang, and they burn it. Nuclear fusion in stellar cores converts hydrogen into helium, releasing energy as light and heat at a rate so enormous that a single star radiates more energy in 1 second than the entire human civilization has consumed in all of history. The process is slow by stellar timescales. A star like our own will burn hydrogen steadily for roughly 10 billion years before its fuel runs low. But over those 10 billion years, it performs an extraordinary transformation. It converts the lightest and most abundant element in the universe into the heavier elements that make complex chemistry possible. When hydrogen runs low in a stellar core, the star does not simply stop. Gravity compresses the helium-rich core, raising its temperature until helium itself begins to fuse into carbon and oxygen, the backbone elements of organic chemistry. More massive stars continue further, fusing carbon into heavier and heavier elements in a sequence of shells, each layer burning a heavier fuel until at the center sits an iron core. Iron is the endpoint of exothermic stellar fusion. When iron core forms, the nuclear burning that has held the star up against gravity suddenly stops, and the star collapses in milliseconds. The outer layers crash inward, bounce off the hardening core, and explode outward in a supernova. Supernovae are the universe's most important chemical events. The explosion disperses into the surrounding interstellar medium all the elements forged over the star's lifetime. The carbon, oxygen, nitrogen, silicon, iron, along with additional elements synthesized in the explosion itself by the extreme conditions of the shockwave. A single supernova scatters into space, a mass of heavy elements greater than the mass of our entire star. That material mixes with the surrounding gas. The next generation of stars and planets forms from this enriched mixture. Each cycle of stellar birth and death adds to the chemical complexity of the interstellar medium, building from the simplicity of hydrogen and helium toward the richness of a periodic table of 92 naturally occurring elements. This cycling of matter through stellar processes is a metabolism in the literal sense. Energy is captured from the gravitational potential of collapsing gas, converted by nuclear processes into electromagnetic radiation and radiated into space. The byproducts, heavy elements, are not waste but feedstock for the next cycle. Each generation of stars builds on the chemical legacy of the previous generation. The process is cumulative and directional. It moves from simplicity toward complexity, from a universe of hydrogen to a universe of carbon-based chemistry, driven not by any goal but by the specific physics of nuclear forces and gravity operating together for billions of years. The universe is building toward chemistry, not because it wants to, but because the machinery it runs on has that consequence built in. The first generation of stars that formed in the early universe would be unrecognizable to a modern astronomer. They formed from pure hydrogen and helium, the only elements that existed in the universe before stellar nucleosynthesis had run for even a single generation. Without heavier elements present in the gas, without carbon, oxygen, and the other elements that modern gas clouds contain, the cooling mechanisms that allow gas to collapse into small stars like our own were absent. The gas clouds that condensed in the young universe collapsed into objects of extraordinary mass, hundreds of times the mass of our own star, burning with a ferocity and a brevity that left them no time to be gentle. These first stars burned at surface temperatures so high they emitted primarily in the ultraviolet, radiating intensely at wavelengths that ionize hydrogen. The radiation from the first generation of stars reionized the neutral hydrogen gas that had filled the universe since the cosmic microwave background was emitted, carving out bubbles of ionized plasma around each star. As more stars formed, the bubbles expanded and merged, and the universe transitioned from the opacity of neutral gas to the transparency of ionized plasma, a phase called the epoch of reionization, which occurred roughly 1 billion years after the Big Bang. The universe we can observe today, filled with transparent intergalactic gas and the light of billions of galaxies, is the product of that transition. The first stars died violently and quickly. Their enormous masses meant they burned through their fuel in a few million years, a cosmically brief existence compared to the billions of years that subsequent smaller stars would achieve. When they collapsed, the supernovae they produced were of unprecedented energy, releasing enormous amounts of heavy elements into the surrounding gas. Some of the most massive first stars may have collapsed directly into black holes, so massive they did not fully explode, but instead swallowed themselves, leaving behind nothing but gravity. But many of them did explode, and those explosions were the first dispersal of heavy elements in the history of the universe. The second generation of stars that formed from the enriched gas was fundamentally different. Heavier elements radiate energy much more efficiently than hydrogen, allowing gas to cool to lower temperatures before collapsing. This means the second generation gas clouds could collapse into smaller, denser objects. Stars more like those we observe today, including some in the range of masses where stars burn for billions of years rather than millions. Around some of those second-generation stars, the heavy elements scattered by the first generation gathered into solid bodies. Planets formed. For the first time in cosmic history, there were stable surfaces, liquid water in temperature ranges compatible with complex chemistry, and the chemical ingredients needed for biological processes. The universe was building towards something, not because it intended to, but because the specific physics of stellar evolution has that consequence when run long enough. In the first fraction of a second after the Big Bang, in a time interval so brief that no comparison, in ordinary experience, captures its brevity, the universe underwent a phase of exponential expansion called cosmic inflation. Space itself expanded at a rate vastly exceeding the speed of light. The distance between every pair of points in the universe doubled, and then doubled again, and then doubled again, over a time so short that even the most rapid atomic processes are glacially slow by comparison. A region of space, smaller than any particle we have ever detected, inflated, in that time, to something roughly the size of a piece of fruit. And the energy driving this expansion, stored in a hypothetical quantum field called the inflaton, eventually decayed, converting into the particles that became everything in the observable universe. Why did inflation happen? The leading answer involves the inflaton field, which permeated early spacetime with an enormous energy density that drove the exponential expansion. When the inflaton decayed, when it fell from its high energy state to a lower one, inflation ended and the energy released became photons, quarks, leptons, and eventually every particle in the universe. But this is a description, not an explanation. We do not know why the inflaton existed, where it came from, or what it is at a fundamental level. It is a hypothetical construct, inferred from its effects. Inflation is supported by strong observational evidence, but its mechanism remains unknown. The evidence is compelling because inflation explains several otherwise inexplicable features of the universe. The cosmic microwave background is almost perfectly uniform in temperature across the entire sky, including regions that were never in causal contact, according to the standard non-inflationary picture. Before inflation, the entire observable universe was contained within a tiny region small enough for thermal equilibrium to be established. Inflation then stretched this equilibrated region to the size of the observable universe, carrying its uniformity with it. The flatness of space, the fact that the geometry of the universe is neither positively curved like a sphere, nor negatively curved like a saddle, but precisely flat, is also explained by inflation, which stretches any initial curvature toward flatness, the way a wrinkled balloon smooths as you inflate it. And the scale invariant spectrum of density fluctuations that seeded all structure in the universe matches the predictions of inflationary models precisely. But inflation has a troubling implication. In quantum mechanics, fields decay through quantum fluctuations, locally, not uniformly. The inflaton decayed in our region, inflation ended here, and our universe formed. In the vast regions surrounding our bubble, the inflaton had not yet decayed. Inflation continued there, and continues still, generating new decay events, new bubble universes, in an endless cascade. This is eternal inflation. Our universe is one bubble in an infinite, ever-growing sea of bubble universes, each forming at a different time, each expanding into its own vast history, each causally isolated from every other. The geometry of space-time ensures we can never see any of the other bubbles. Their light can never reach us. We are separated by distance and also by the structure of space-time itself, and whether those other bubbles have the same physical constants as ours, or different ones, is a question whose answer would determine whether the fine-tuning problem has a natural explanation or remains mysterious. When astronomers built the first large three-dimensional maps of the universe in the 1980s and 90s, surveys covering millions of galaxies across volumes spanning hundreds of millions of light-years, the picture that emerged was not what anyone expected. Galaxies were not scattered randomly. They were not distributed uniformly. They were arranged in an intricate, three-dimensional web of filaments and sheets surrounding vast, nearly empty voids. Galaxy clusters sat at the nodes where filaments intersected. Sheets of galaxies formed the walls between voids. The voids themselves stretched for hundreds of millions of light-years, containing almost nothing. A few isolated galaxies, but mostly empty space. This structure, the cosmic web, is the largest organized structure known to exist. It spans scales that make entire galaxies look like specks of dust. It was not designed. It emerged, over billions of years, from the interaction of gravity and the density fluctuations seeded by inflation. Slightly denser regions attracted more dark matter, which attracted more ordinary matter, which attracted still more dark matter in a feedback loop that ran for billions of years, accumulating mass into filaments and nodes while leaving the regions between them increasingly empty. The specific pattern of the web carries information about the initial density fluctuations, about the ratio of dark matter to ordinary matter, and about the history of the expansion. Cosmologists study it the way geologists study rock strata, as a record of the forces that shaped the universe. What makes the cosmic web remarkable beyond its size is a statistical coincidence that has drawn serious scientific attention. When researchers compared the quantitative properties of the cosmic web with the quantitative properties of the neuronal network of the human brain, measuring things like the distribution of connection strengths, the clustering of nearby nodes, the ratio of dense clusters to empty voids, they found specific, measurable, statistical similarities. The two systems, separated in scale by roughly 27 orders of magnitude, exhibited similar network statistics. The researchers were careful not to overclaim. The similarity does not mean the universe is conscious. It does not mean the brain is cosmological. It means the same mathematical principles of network self-organization appear to operate across scales from neurons to galaxy clusters. This is actually less surprising than it first appears, and more interesting. Both the brain's neuronal network and the cosmic web are products of a limited set of organizing principles, a large number of nodes connected by pathways, with growth of new connections governed by local interactions, producing hierarchical clustering and efficient long-range communication over time. These are very general properties of self-organizing networks. The same principles produce similar statistical signatures regardless of the specific physical substrate. What is interesting is that the universe's self-organization, driven by gravity and dark matter, produces network statistics similar to those produced by biological evolution and neural development. The universe builds networks according to the same abstract rules at every scale it has organized. Nobody has a complete explanation for why. The anthropic principle was formulated precisely by physicist Brandon Carter in the 1970s, though the underlying idea is much older. In its weak form, it says simply, we can only observe a universe compatible with our existence. If the universe did not have properties that permit observers, there would be no observers to note the fact. This sounds like a truism, and in a sense it is. but it has a non-trivial implication that took time to appreciate. The anthropic principle is sometimes used to explain fine-tuning. Why do the constants have values that permit observers? Because if they did not, there would be no one to observe them. This explanation is logically valid. It is also deeply unsatisfying to many physicists, because it does not explain why a universe with observer-compatible constants exists at all. It only establishes that, if any observer-compatible universe exists, the observers in it will observe observer-compatible constants. What it does not explain is why there is at least one such universe. For the anthropic explanation to do real explanatory work, you need a large ensemble of universes with varying constants, so that there are enough universes to make it unsurprising that at least one of them is compatible with observers. Without the ensemble, the anthropic principle explains nothing. With an ensemble, whether the string landscape or the bubble universes of eternal inflation, the anthropic principle becomes a genuine probabilistic argument. If there are vastly many universes with different constants, and if the distribution of constants across those universes is broad enough to include our values, then it is not surprising that we find ourselves in a universe with our constants. We are a sample from the distribution, and we are necessarily in a compatible region of the distribution. The argument works. The problem is that it works too well. An explanation that explains why our universe has any set of observer-compatible constants, regardless of which specific set, is an explanation that makes no specific predictions. It predicts only that we find ourselves in some universe that permits observers. Every feature of our universe that goes beyond mere compatibility with observers, the specific value of the nuclear force, the specific density of dark matter, the specific geometry of the cosmic web, is left unexplained. The anthropic principle plus a large ensemble is less an explanation than a framework for why no specific explanation is needed. Whether that is acceptable depends on whether you think science should explain specific features of our universe or merely show that some universe compatible with observers is possible. Smolin's cosmological natural selection claims to do better by proposing a specific mechanism, selection for black hole production. It predicts that we exist, and also that our constants are near optimal for a specific physical process. This is a prediction beyond what the anthropic principle alone can make. Whether it is the correct explanation, whether the selection mechanism is real, whether the constants are actually near the optimum for black hole production, these are questions that can be investigated, even if the investigation is technically demanding. And that distinction between an explanation that makes specific testable predictions and one that merely shows existence is possible is the heart of the debate between the string landscape and cosmological natural selection that drives theoretical cosmology today. The first generation of stars that ignited in the young universe burned in a cosmos completely unlike ours. The universe was roughly 100 million years old, still dark in most places, still cooling from the fireball of the Big Bang. Neutral hydrogen and helium filled the space between sparse concentrations of dark matter that had been slowly accumulating under gravity. There was no carbon, no oxygen, no nitrogen, no iron, none of the heavy elements that modern gas clouds contain, because heavy elements are made inside stars, and no stars had yet died. The absence of these heavier elements meant the gas could not cool as efficiently as it does today. Cooling is what allows gas to compress into dense objects. Without efficient cooling, only very massive gas clouds could collapse under their own gravity, and they collapsed into very massive stars. The first stars were monsters. Their masses ranged from tens to possibly thousands of times the mass of our own star, depending on conditions. They burned at temperatures so extreme, their surfaces radiated primarily ultraviolet light, radiation energetic enough to ionize the hydrogen gas surrounding them. Each massive star carved a bubble of ionized plasma in the surrounding neutral hydrogen, and as more stars formed, these bubbles expanded, merged, and eventually filled the entire universe with ionized intergalactic gas. This process, called cosmic reionization, transformed the universe from opaque to transparent for the second time in its history, the first being the formation of neutral atoms that produced the cosmic microwave background. The reionized universe we observe today, transparent and filled with the light of billions of galaxies, is a consequence of the radiation from the first generation of stars. Those first stars lived briefly and died violently. Their enormous masses meant their fusion ran at a furious rate, consuming their fuel in a few million years. By comparison, a star like our own burns steadily for 10 billion years. When the first stars exhausted their fuel, their cores collapsed and they exploded in supernovae of unprecedented energy. Some were so massive they may have collapsed entirely into black holes, contributing to the first generation of stellar mass black holes. Others exploded and scattered into the surrounding gas, the first heavy elements the universe had ever seen: carbon, oxygen, nitrogen, magnesium, silicon, iron. That dispersal was the first step in building the chemical complexity that eventually produces chemistry, biology, and minds. The second generation of stars, forming from the enriched gas left by the first, was fundamentally different. The presence of heavy elements gave the gas new ways to radiate energy. Carbon, in particular, is an excellent coolant at the temperatures where star-forming clouds collapse. Gas enriched with even tiny amounts of carbon could cool more efficiently, allowing smaller and more stable clouds to collapse. The second generation included stars across a wider range of masses, including some similar in mass to our own star: modest, long-lived, stable objects capable of burning for billions of years. Around some of those stars, the heavy elements scattered by the first generation gathered under gravity and built up solid bodies. Planets formed for the first time. The universe was not merely expanding and cooling, it was building. Consciousness is something the universe clearly produces. You are conscious, and you are made of the same atoms as everything else. Whatever consciousness is at the physical level, it is a real phenomenon that occurs in a universe whose fundamental laws, as we currently write them, make no reference to experience. The equations of quantum mechanics describe particles and fields and their interactions without mentioning what it is like to be anything. General relativity describes the curvature of space-time without reference to subjective experience. The standard model of particle physics is a complete description of the fundamental constituents of matter and their interactions, and it contains nothing that corresponds to the feeling of seeing red, or the experience of hunger, or the sense that you exist and are thinking these thoughts. Yet, you experience all of those things. The universe runs on physics that does not mention experience, and yet experience happens. Somewhere between the equations and the reality, something is being left out. And the question of what is being left out, the question of why physical processes produce subjective experience at all, is the hardest problem in science, not the hardest unsolved problem in a particular field. The hardest problem across all of science, the one with the least progress and the most fundamental implications. Neuroscience can describe the correlates of consciousness in extraordinary detail. It can tell you which brain regions are active during different types of experience, which neural oscillations are associated with awareness, what happens to brain activity under anesthesia or dreamless sleep. These correlates are real and informative, but identifying what physical activity correlates with consciousness is not the same as explaining why that activity produces consciousness. You can map every neural circuit involved in the experience of seeing blue and still have no explanation for why those circuits produce a qualitative experience of blue rather than just an information processing state that responds to blue wavelengths. The gap between the physical description and the experiential reality is, as far as current theory goes, unbridgeable. Panpsychism is one of the oldest and also one of the most recently revived philosophical positions on consciousness. It holds that consciousness is not produced by matter at some threshold of complexity, but is fundamental to matter at all levels. Electrons do not have rich experiences with emotional content. but they have some most primitive form of what might be called interiority, some minimal responsiveness that is not merely mechanical. At higher levels of organization, this primitive property combines into increasingly complex forms. Human consciousness is what this fundamental property looks like when organized into a system of roughly 100 billion neurons with trillions of synaptic connections, extensive feedback loops, and the capacity for recursive self-modeling. The hard problem of consciousness disappears, on this view, not because it is solved, but because its premise that consciousness has to be generated from something that is not conscious is rejected. For most of the 20th century, panpsychism was dismissed as obviously wrong. In the last 2 decades, it has come back into serious philosophical and even scientific discussion, partly because the hard problem has proven so completely resistant to standard approaches, and partly because a rigorous mathematical framework, integrated information theory, has given it a basis for making specific predictions. Integrated information theory was developed by neuroscientist Giulio Tononi, originally as an attempt to understand consciousness in terms that could be measured and tested rather than simply described philosophically. The theory's central quantity is phi, a number that measures how much information a system generates as a whole, above and beyond what its parts generate independently. A system with phi greater than 0 is, according to the theory, conscious to some degree. A system with phi equal to 0 has no experience. The larger the phi, the richer and more complex the conscious experience. To understand what phi means, consider 2 contrasting examples. A camera is a large array of light-sensitive elements, each measuring the brightness at one point in the image. The elements are largely independent. Each pixel reports its value without any complex interaction with the others. The whole camera does not generate much information beyond what the sum of its pixels generates. Phi is low. The camera has, according to IIT, essentially no experience. A human brain, by contrast, is a massively interconnected system where every region influences every other. The visual cortex feeds information to the prefrontal cortex, which feeds back to the visual cortex, which connects to memory systems, which connect to emotional centers, which modulate attention, which affects visual processing. The whole generates information that could not be predicted from any subset of the parts. Phi is very high. According to IIT, this high phi corresponds to the rich, conscious experience of being a person. The theory makes specific predictions about which physical systems should be conscious. A brain region during dreamless sleep has lower phi than during alert wakefulness, consistent with the reduced or absent experience during deep sleep. The theory predicts that gradually severing connections between brain regions should reduce phi and, correspondingly, reduce conscious experience. It predicts that certain apparently complex systems, very large but modular systems with relatively little internal integration, will have low phi and little or no consciousness. These predictions are in principle testable, and some have been tested, with results that Tononi and collaborators consider supportive. The strongest objection to IIT is also the most vivid. The computer scientist Scott Aronson demonstrated that the theory implies very simple computational systems, large arrays of logic gates performing certain types of computation, could have very high phi and therefore, on the theory's account, a rich, conscious experience. This seems intuitively wrong. Logic gates are not having experiences. Spreadsheets calculating thousands of cells simultaneously are not conscious. Aronson's objection points to a potentially deep flaw in the theory. Tononi's responses have partially addressed the objection, but not fully resolved it. The theory remains controversial among physicists, neuroscientists, and philosophers of mind. But whatever the ultimate status of IIT, it does something important that previous approaches did not. It provides a mathematical framework for asking whether any physical system is conscious, and it makes specific predictions about the properties of physical systems that distinguish conscious from non-conscious ones. Applied to the universe, it raises a question that had previously been purely metaphorical. Given the deep integration of the universe as a physical system, the gravitational connections between all its parts, the pervasive cosmic microwave background, the quantum entanglements extending across its entire history, does the universe have phi? Is there, in the most primitive possible sense, something it is like to be the universe? The honest answer is that the calculation has not been performed, and the framework is contested. But the question is no longer entirely outside the domain of science. For the first 380,000 years after the Big Bang, the universe was opaque. Not dark, but opaque. The distinction matters. The universe was filled with an extraordinarily hot plasma, a dense fog of protons, electrons, and photons in constant interaction. Photons could not travel far in this plasma before colliding with an electron and being absorbed and re-emitted. Light was trapped in the plasma the way light is trapped inside a dense fog bank, constantly scattered, unable to travel freely in any direction. The universe was bright in every direction, but you could not see anything through it. Every line of sight disappeared into the glow of the surrounding plasma within a short distance. This plasma-opaque era lasted for 380,000 years. The universe expanded and cooled throughout this time. When the temperature dropped to roughly 3,000 degrees, hot enough to melt steel many times over, but cool by cosmic standards, a transition occurred. At this temperature, electrons had slowed down enough that they could be captured by protons and form neutral hydrogen atoms. Neutral atoms do not interact with photons the way free electrons do. The plasma suddenly became a gas of neutral atoms, and the photons that had been trapped in the plasma were released to travel freely for the first time. The universe became transparent in a geological instant. Those photons are still traveling today. They have been crossing the universe for over 13 billion years, and they reach our detectors from every direction simultaneously. The expansion of the universe has stretched their wavelengths from the high-energy visible and near-infrared of a 3,000-degree gas to the low-energy microwave frequencies they carry today. We call this the cosmic microwave background. It is the universe's oldest light, a snapshot of conditions when the universe was 380,000 years old, and it is one of the most information-rich objects in observational cosmology. Every direction in the sky glows in microwave frequencies at almost exactly the same temperature, about 2.7 degrees above absolute zero. The uniformity is extraordinary, 1 part in 100,000. But within that uniformity are tiny variations. The cosmic microwave background is not perfectly uniform. It has hot spots and cold spots, slightly denser and slightly less dense regions, at a level of 1 part in 100,000. These tiny temperature fluctuations are the fingerprints of quantum fluctuations in the inflation field, stretched to cosmic scales during inflation. They are the seeds from which all structure in the universe grew. Every galaxy, every star, every planet traces its origin to a temperature fluctuation in the cosmic microwave background. A quantum ripple in the earliest history of the universe, stretched to cosmic scale and then amplified over billions of years by gravity into the elaborate structures we see today. 380,000 years after the Big Bang, the universe was a nearly uniform gas of neutral hydrogen and helium, with tiny density fluctuations. The 1 in 100,000 variations imprinted in the cosmic microwave background. From that almost featureless starting point, gravity spent the next several billion years building everything. The process was not fast by human standards, but it was inexorable. Gravity never rests. Every region, even slightly denser than its surroundings, attracted more matter. More matter made it denser still. The feedback was positive. Denser regions grew denser. Emptier regions grew emptier, over millions and then billions of years. Dark matter was the leading actor in this process. Dark matter does not interact with light or with ordinary matter, except through gravity. It does not emit, absorb, or scatter photons, but it responds to gravity and generates gravitational attraction. In the early universe, when ordinary matter was still coupled to the photon gas, still interacting with the radiation that filled the plasma, dark matter was free to start clustering. It began to form the first gravitational structures before ordinary matter could, building invisible scaffolding into which ordinary matter later fell. The first large-scale structures in the universe were dark matter halos, gravitational wells in the distribution of dark matter, not yet containing any ordinary matter, simply concentrated regions of gravitational potential waiting to be filled. When ordinary matter decoupled from the photon gas at recombination, when the universe became transparent, it began to fall into the dark matter scaffolding. Gas flowed along dark matter filaments, accumulating at the intersections. In the densest intersections, the gas became dense enough and hot enough for nuclear fusion to ignite. The first stars appeared, then the first small galaxies formed around these first stars. Then larger galaxies formed as smaller ones merged and accumulated more gas. The process built hierarchically, from small to large, over hundreds of millions to billions of years, producing the galaxy-sized structures we observe today inside dark matter halos, containing 10 to 100 times as much dark matter mass as stellar mass. The result of this billions of years process is the cosmic web, the intricate three-dimensional network of galaxy filaments and voids that constitutes the large-scale structure of the universe. Every galaxy visible in the night sky sits inside a dark matter halo. Every galaxy cluster sits at the intersection of dark matter filaments. The voids between the filaments are largely empty. Most of the matter has been swept up into the filaments and nodes over billions of years of gravitational accumulation. The universe has organized itself from near-perfect uniformity into a complex structure spanning hundreds of millions of light-years, driven by nothing more than gravity acting on a slightly uneven distribution of matter, seeded by quantum fluctuations in the first fraction of a second after the Big Bang. The scale of the organization is extraordinary. The mechanism is elegantly simple. Dark matter is one of the most firmly established facts in modern cosmology. The evidence for its existence is overwhelming, coming from multiple, completely independent observations that all point to the same conclusion. And dark matter is also one of the most embarrassing mysteries in physics. We know it is there. We know roughly how much of it there is. We know where it is distributed. We cannot identify what it is made of. The first strong evidence for dark matter came from the rotation curves of galaxies. When astronomers measure the speeds at which stars orbit the center of a galaxy at different distances from the center, they expect to find a pattern similar to our solar system. Objects farther from the center orbit more slowly, just as the outer planets orbit more slowly than the inner ones. This is what Newtonian gravity predicts for a mass concentrated near the center. But galaxies do not behave this way. Stars in the outer parts of galaxies orbit at roughly the same speed as stars near the center, regardless of their distance. The rotation curve is flat where it should fall off. The only way to explain this with gravity as we understand it is to suppose there is a vast halo of invisible mass surrounding every galaxy, providing additional gravitational pull to keep the outer stars moving at the speeds we observe. Independent confirmation comes from gravitational lensing. When light from a distant object passes near a massive foreground object, the mass bends the light's path. Gravitational lensing, predicted by general relativity and confirmed to high precision. By measuring how much a galaxy cluster bends the light of more distant background galaxies, astronomers can calculate the total mass of the cluster. The answer is consistently much larger than the mass in visible stars and gas. Somewhere between 5 and 10 times as much mass is present as the visible material can account for. That extra mass is dark matter. The formation of cosmic structure provides a third line of evidence. Building the observed cosmic web from the tiny density fluctuations in the early universe requires a component of matter that can begin clustering before ordinary matter does. and that provides the gravitational scaffolding for ordinary matter to fall into. Dark matter, which does not interact with the photon gas in the early universe and can therefore start clustering early, provides this scaffolding perfectly. Models of cosmic structure formation that include dark matter in the observed quantities match the observed cosmic web with great precision. Models without dark matter do not. Despite this overwhelming evidence for dark matter's existence, no experiment has directly detected a dark matter particle. Detectors buried deep underground to reduce cosmic ray interference, looking for the rare collision of a dark matter particle with an atomic nucleus, have found nothing. Particle accelerators energetic enough to produce dark matter particles, if the most popular theoretical models are correct, have found nothing. Gamma-ray observations searching for the energetic photons that dark matter self-annihilation would produce have found no convincing signal. The most theoretically favored dark matter candidates have been progressively ruled out at the parameter values where they were expected to appear. Dark matter, whatever it is more elusive than our best theories predicted. In the late 1990s, two independent teams of astronomers were measuring distances to distant supernovae. These supernovae, produced when aging stars explode after accumulating too much mass, have a reliably consistent peak brightness, which makes them useful as distance markers. By measuring how bright a distant supernova appears, you can calculate how far away it is. By measuring how fast the galaxy containing the supernova is receding from us, you can measure how fast the universe was expanding when the supernova's light was emitted. Comparing distances and recession speeds at different epochs allows you to track how the expansion has changed over time. Both teams expected to find evidence of the expansion slowing down. The universe is full of matter, and matter gravitates. Gravity should be pulling things together, working against the expansion, causing it to decelerate over time. The question was how much deceleration, not whether there was deceleration. Both teams prepared to measure the rate of slowdown. What they found was that distant supernovae were dimmer than expected, farther away than they would be in a decelerating universe. The universe was not decelerating, it was accelerating. The expansion was faster at late times than at early times. Something was pushing space apart with increasing force, working against gravity at the largest scales, driving the universe to expand faster as time went on. Both teams initially suspected systematic errors. The result was so unexpected that neither group was confident enough to publish it without extensive checking. They checked their calibrations, their distance measures, their observational techniques. The result stood. In 1998, both groups published their findings. The expansion of the universe was accelerating. The discovery earned its lead authors the Nobel Prize in Physics in 2011. The force driving this acceleration is called dark energy. It constitutes roughly 68% of the total energy content of the universe. Ordinary matter, everything you can see, touch, or detect by any means, is about 5%. Dark matter is about 27%. The dominant component of the universe, the force actively reshaping its geometry and determining its eventual fate, is completely unknown in its fundamental nature. We know it exists because of what it does. It accelerates the expansion. We do not know what it is. The theoretical candidate for dark energy is the cosmological constant, a fixed energy density associated with empty space, representing the energy of quantum vacuum fluctuations. Einstein introduced the cosmological constant, then abandoned it. Then the universe turned out to need it. The problem is that quantum field theory predicts a vacuum energy density roughly 10 to the 120th power times larger than what observations require. This is the cosmological constant problem, the largest discrepancy between theory and observation in all of science. Either something cancels the quantum vacuum energy almost perfectly to 1 part in 10 to the 120 by a mechanism completely unknown, or our theory of vacuum energy is wrong in a way we have not identified. Both options require fundamental revisions to our understanding. Dark energy is not a footnote. It is a signal that something about our deepest theories of nature is profoundly wrong. Physics is built on two extraordinary foundations. Quantum mechanics describes the behavior of everything at the subatomic scale with an accuracy that is, without exaggeration, the most precisely verified theory in all of science. The predictions of quantum electrodynamics, the quantum theory of electromagnetism, have been tested to 12 decimal places. General relativity describes gravity and the large-scale structure of space-time, and has been verified with equal precision at the scales where it applies. The orbits of planets, the bending of light by massive objects, the gravitational waves from colliding black holes. Both theories are triumphs of human understanding. Both are extraordinarily accurate, and they are fundamentally incompatible with each other. The incompatibility is not a practical problem in most circumstances. Quantum mechanics operates on the very small. General relativity operates on the very large. In the middle range, the range where most physics happens, the two theories rarely need to talk to each other. Atoms are too small for general relativity to matter. Galaxies are too large for quantum mechanics to matter. In the everyday world, you can use one theory or the other, depending on the scale of the problem, and never encounter the conflict. The conflict becomes real and unavoidable in two circumstances: the extreme densities at the center of a black hole and the extreme conditions of the very early universe. Both situations involve matter compressed to densities where the quantum effects of space-time itself become important, where gravity is strong enough that quantum mechanics cannot ignore it, and quantum effects are strong enough that gravity cannot ignore them. These are the domains where a unified theory, a quantum theory of gravity, is essential, and where neither quantum mechanics nor general relativity, applied separately or combined naively, give sensible answers. The black hole singularity is the most vivid example of where the conflict matters. General relativity predicts a singularity. Quantum mechanics has a principle, unitarity, that information is never destroyed. If the singularity destroys information about the matter that fell into the black hole, quantum mechanics is violated. If information is somehow preserved, general relativity's description of the black hole interior must be wrong. Both options require revising one of our most successful theories. The information paradox is not merely a technical puzzle. It is a signal that our current understanding of physics is fundamentally incomplete at the intersection of its two best theories. The pursuit of a quantum theory of gravity is one of the central challenges of contemporary theoretical physics. Loop quantum gravity and string theory are the two leading approaches, and they make different predictions about the physics of black hole interiors, the resolution of singularities, and the nature of space and time at the smallest scales. Loop quantum gravity predicts that singularities are replaced by quantum bounces, the mechanism that might enable cosmic reproduction in Smolin's model. String theory predicts that the black hole interior is related to the exterior through the holographic principle, with the information on the event horizon encoding everything inside. Both predictions are in principle observable. If only we could observe the interior of a black hole. We cannot. The resolution of the information paradox and the correct theory of quantum gravity remain unknown. The multiverse from eternal inflation is not a speculative add-on to inflationary cosmology. It is an almost unavoidable consequence of the physics that makes inflation work. Understanding why requires understanding what inflation is and how it ends. Inflation is driven by a scalar field, the inflaton, in a high energy state. The field has a potential energy that drives the exponential expansion of space. As the field rolls down its potential, decreasing its energy, inflation slows and eventually ends. In our region of the universe, the inflaton reached a low energy state roughly 10 to the negative 32 seconds after the Big Bang. Inflation ended. The energy released became the particles that fill the universe. All of this is standard inflationary cosmology, supported by observations. The problem arises from quantum mechanics. In quantum field theory, fields do not change uniformly everywhere. They fluctuate. Quantum fluctuations in the inflaton field can, in some regions, push the field back up its potential rather than allowing it to roll down. In those regions, inflation continues rather than ending. The probability of such a quantum fluctuation is small in any given region, but inflation is expanding the volume of the inflating region exponentially. New volume is being created faster than inflation ends in any given small region. The total volume that is still inflating grows exponentially without bound. Inflation, once started, generates new inflationary volume faster than it loses inflationary volume to bubble formation. It never stops globally. This is eternal inflation, and it implies that our universe, our bubble, is one among an infinite, ever-growing collection of bubbles, each forming when the inflaton decays in a local region, each expanding into its own vast cosmic history, each forever causally separated from every other. The bubbles are not arranged spatially like soap bubbles in a foam. They are separated by regions of still inflating space that are themselves expanding faster than light. No signal from any bubble can reach any other. Each bubble is, from the inside, an entire universe with its own past, its own future, its own physical laws. The question of whether the physical laws differ from bubble to bubble depends on the structure of the inflaton potential, specifically, whether the inflaton can settle into different low-energy states in different bubbles, each corresponding to different effective physical constants. In the context of string theory, which predicts an enormous landscape of possible low-energy states, the answer is yes. Different bubbles land on different points in the landscape and acquire different physical constants. In the context of other models of inflation, the constants might be the same in every bubble. The distinction matters enormously for the explanation of fine-tuning. If constants vary across bubbles, the anthropic landscape explanation works. If they do not, fine-tuning remains unexplained, and Smolin's natural selection becomes more important. The string theory landscape emerged from an unexpected turn in the history of string theory. String theory was originally developed in the hope that it would derive a unique set of physical constants that the mathematical consistency requirements of a theory of vibrating strings would force a specific set of particle masses, force strengths, and other parameters. The expectation was that the theory would explain why the constants are what they are by showing that they could not be anything else. Instead, string theory revealed an enormous space of possible solutions. The extra dimensions that string theory requires, beyond the three spatial dimensions we experience, can be curled up in an astronomically large number of ways, each yielding different effective physics in the three large dimensions. The number of possible configurations is roughly 10 to the power of 500. This collection of possible solutions is the landscape. Rather than predicting a unique set of constants, string theory predicts that all possible sets of constants compatible with the mathematical structure of the theory are realized somewhere. The universe we observe corresponds to one specific configuration of the extra dimensions, but there is nothing in the theory that singles out our configuration as special. Every configuration is equally valid from the theory's perspective. This was initially seen as a disaster for string theory, an indication that the theory was too broad to be predictive. Physicist Leonard Susskind reframed it as a solution to fine-tuning. If there is an enormous landscape of possible physics and eternal inflation generates a universe exploring every point in that landscape, then the question of why our universe has its specific constants has the same answer as the question of why a specific lottery ticket was drawn. With enough tickets, every number eventually comes up. We are in a bubble that happened to land on constants compatible with our existence. Given the size of the landscape, it is essentially guaranteed that some bubbles are compatible with observers. We find ourselves in one such bubble because we cannot be in any other. The response from Lee Smolin and others was sharp. The landscape plus anthropic principle explains why we exist but predicts nothing about which specific constants we should observe. There are presumably many different configurations compatible with the existence of observers, each with slightly different constants. Without knowing the probability distribution of constants across the landscape, which requires knowing the details of the landscape measure problem, an unsolved technical issue in string theory, the landscape cannot predict which observer-compatible configuration we should expect to find ourselves in. The theory is consistent with any set of observer-compatible constants. It makes no prediction that can distinguish our constants from any other compatible set. Smolin argues this means the landscape, as an explanation, is empty. It explains the existence of observers but explains nothing specific about the universe. Observers actually inhabit. Suskind's counter is that making predictions about which set of compatible constants we should expect requires solving the measure problem, and that the measure problem, while unsolved, is in principle solvable. A solved measure problem might single out specific regions of the landscape as more probable, making specific predictions about constants. Until the measure problem is solved, the landscape remains an incomplete explanation, but not an empty one. The debate continues, and its resolution, if it comes, may require observational evidence that current experiments cannot provide. Lee Smolin and Leonard Susskind represent two of the most thoughtful positions on one of the deepest questions in physics. Both accept that the constants are finely tuned. Both accept that a multiverse of some kind is probably involved in the explanation. They disagree fundamentally on what an explanation should look like and how science should proceed when the objects of explanation, other universes, are, in principle, unobservable. Suskind's position is essentially that the string landscape, combined with eternal inflation, is the best explanation currently available for fine-tuning. It is derived from our best mathematics. It is consistent with everything we observe, and it makes the fine-tuning problem tractable by providing a framework in which it is unsurprising that our universe has life-compatible constants. Susskind acknowledges that the theory does not make specific predictions about which set of compatible constants we should expect. He argues this is a temporary limitation, not a fundamental one. As string theory develops and the measure problem is better understood, more specific predictions may become possible. Smolin's position is that a theory that cannot make specific testable predictions is not doing science in the sense that has made science so productive. The hallmark of a good scientific theory is that it rules things out, that it predicts some observations rather than others, that it could in principle be wrong. A theory consistent with any observer-compatible universe, including any set of observer-compatible constants, does not rule anything out. It is immune to falsification in a way that should make scientists uncomfortable. Smolin argues that cosmological natural selection, despite its own gaps and uncertainties, is more scientifically valuable because it makes specific predictions. Our constants should be near optimal for black hole production. This prediction can be checked. The theory can be wrong, and that vulnerability to being wrong is, Smolin argues, what distinguishes science from philosophy. The deeper issue is about what it means for something to be explained. Suskind's landscape says the constants are explained by their place in an ensemble where all compatible configurations exist. The explanation is structural. Given the landscape, it is not surprising that some configurations are compatible with observers, and we find ourselves in one. Smolin's natural selection says the constants are explained by their history. They are what they are because universes with these constants reproduced more than universes with other constants. The explanation is historical. The constants have the values they have because they were the winners of a competition. Both types of explanation appear in science. Population genetics explains the frequencies of genetic variants, partly structurally. Given a gene pool, some distributions are more probable, and partly historically. The current distribution reflects the specific history of selection pressures acting on this particular lineage. Both types of explanation can be valid. The question is, which applies to universes? And answering that question requires either developing the landscape measure problem or testing the predictions of cosmological natural selection, challenges that will occupy physicists for decades. Every structure in the universe exists because of a fundamental tension between entropy and gravity. Entropy is the tendency of energy to spread uniformly, of disorder to increase, of concentrated things to disperse. Gravity is the tendency of matter to concentrate, to pull toward itself, to accumulate into dense objects. Between these two tendencies, entropy pushing outward and gravity pulling inward, all interesting things happen. Stars burn because they are concentrations of matter, sitting in a gravitational well, dissipating an energy gradient between their hot interiors and the cold void surrounding them. As long as the gradient exists, as long as the core is hot enough to fuse elements and the surrounding space is cold enough to absorb the energy, the star radiates. Life maintains itself by continuously capturing energy from an external source, using it to build and maintain order locally against the global increase of entropy. A living cell is more ordered than the chemicals from which it formed, but the process that builds the cell produces more entropy elsewhere, in the heat it releases, in the waste products it generates. Life is an entropy pump, creating local order at the cost of global disorder, sustained by an energy flow that cannot last forever. The second law of thermodynamics states that entropy always increases in a closed system. This is the deepest statement about the direction of time in all of physics. The past is the direction of lower entropy. The future is the direction of higher entropy. You remember the past but not the future, because the past corresponds to states of lower entropy, and the second law ensures entropy only ever increases. Heat flows from hot to cold, never the reverse. Broken cups do not spontaneously reassemble. Chemical reactions run in the direction of greater disorder. Everything we observe about the direction of time is a consequence of this one law. The universe began, at the Big Bang, in a state of extraordinary low entropy. This is not obvious. The Big Bang was hot and dense, conditions we usually associate with disorder. But the relevant entropy is gravitational entropy, and a smooth, uniform distribution of matter is a low entropy state from the gravitational perspective. When you allow gravity to act on a smooth distribution, it produces clumping, dense regions pulling in matter, empty regions becoming more empty. That clumping is an increase in gravitational entropy. The formation of stars, galaxies, and galaxy clusters represents the universe moving from a smooth, low entropy state to a lumpy, high entropy one. And the universe has been doing this for 14 billion years, with enormous amounts of low entropy room left to fill. The low entropy of the Big Bang is one of the deepest unexplained facts in cosmology. Physicist Roger Penrose calculated the probability of the universe beginning in a state as ordered as it appears to have been. The answer is a number so small that it would require more zeros than there are atoms in the observable universe to write out. The initial conditions of the universe were not merely improbable, they were improbable in a way that makes every other improbability in science look routine. Why the universe started in such an ordered state, and whether this is connected to the fine-tuning problem, is unknown. It may be that the same mechanism that sets the constants also sets the initial entropy, or it may be a separate mystery that requires a separate explanation. Either way, it is one of the deepest puzzles we carry. The far future of the universe follows from thermodynamics with logical inevitability. It has chapters, and each chapter is darker and longer than the last, and the final chapter lasts forever. The first chapter to close will be the age of stars. The most massive stars have already burned out billions of years ago. Stars of moderate mass, like our own, burn steadily for billions of years and then swell into red giants, expelling their outer layers and leaving behind cooling white dwarf cores. The smallest stars, red dwarfs, which constitute roughly 3/4 of all stars in the galaxy, burn so slowly and so efficiently that some will still be fusing hydrogen roughly 10 trillion years from now. 10 trillion years. The current age of the universe is roughly 14 billion years. The last red dwarf will outlive our era by a factor of about 700. When the last star burns out, the galaxy will not go dark instantly. It will fade over immense timescales as the stellar remnants cool. White dwarfs radiate heat for trillions of years, slowly dimming from white to yellow to red to invisible. Neutron stars cool similarly. Black holes, which accumulate matter but can also radiate via Hawking radiation, persist far longer. Stellar mass black holes evaporate on timescales of roughly 10 to the 67th years, and supermassive black holes on timescales of 10 to the 92nd years. These are numbers that dwarf even the stellar cooling timescales by factors that have no useful comparison in ordinary language. If protons decay, as many extensions of the Standard Model predict, though none have been confirmed, ordinary matter dissolves. Planets, asteroids, white dwarfs, over a timescale of roughly 10 to the 37th years, every proton in every piece of ordinary matter decays into lighter particles and radiation. The solid material of the universe dissolves into a diffuse fog. What remains are black holes and the products of proton decay, photons, electrons, positrons, neutrinos, dispersed through an ever-expanding universe. The last black holes evaporate through Hawking radiation over timescales of 10 to the 92nd to 10 to the 100th years. When they are gone, the universe contains nothing but an ever-diluting gas of photons, neutrinos, and possibly electrons and positrons, expanding through an ever larger spacetime. Every photon redshifts to longer and longer wavelengths, carrying less and less energy. Every temperature asymptotes toward absolute zero. Every density asymptotes toward zero. The universe reaches maximum entropy, featureless, uniform, thermally dead. This is heat death, and it is as close to nothing as something can get. Not fire and explosion, but stillness and uniformity, stretched over timescales so vast that all of current cosmic history is a rounding error. You exist in the brief, bright, middle chapter of a story that began with the Big Bang and ends with featureless nothing. The chapter you are in, the Age of Stars, is extraordinarily improbable because it requires the specific initial conditions that the universe happened to have, and it is finite because entropy is always increasing. The interesting part of the story is happening now. You are in it. Stephen Hawking's discovery in 1974 that black holes are not black, that they emit radiation and slowly evaporate, is one of the most celebrated results in theoretical physics. It emerged from applying quantum field theory to the curved spacetime surrounding a black hole and finding something nobody expected. Virtual particle pairs, produced by quantum fluctuations near the event horizon, could separate, with one particle escaping and the other falling in. The escaping particle carries energy away from the black hole, repeated over an enormous time span. This process causes the black hole to lose mass. A black hole of the mass of our own star would take roughly 10 to the 67th years to evaporate completely, but evaporate it will. This result changed how physicists thought about black holes fundamentally. Black holes were no longer permanent. They had a lifetime. They had a temperature, the Hawking temperature, inversely proportional to the mass of the black hole, so tiny for large black holes as to be unmeasurable in practice, but real and calculable in principle. And they had an entropy, the Bekenstein-Hawking entropy, proportional to the area of the event horizon in Planck units. The entropy of a black hole is the largest possible entropy for a region of space of that size. A black hole is the most disordered, highest entropy object that can fit within its own boundary. This connection between black holes, thermodynamics, and quantum mechanics hinted that all three are deeply related in a way we do not yet fully understand. The problem Hawking radiation creates is the information paradox. When matter forms a black hole, the information describing the exact quantum state of that matter, every particle's position, momentum, spin, and every other quantum property falls with it into the interior. When the black hole evaporates, the Hawking radiation appears to be purely thermal. It is characterized entirely by the black hole's temperature, which depends only on its mass. It does not appear to carry any information about what fell in. If a book falls into a black hole and the black hole evaporates, the book's content appears to be gone forever. Quantum mechanics says this cannot happen. Information, in quantum mechanics, is always conserved in principle. The information paradox says it was not. Resolving the paradox requires either accepting that quantum mechanics is wrong about information conservation in the presence of black holes, or accepting that general relativity is wrong about the description of the black hole interior, or finding some mechanism by which information is encoded in the Hawking radiation in a way so subtle it appears thermal. Recent work has made progress on the third option, using tools from quantum information theory and holographic ideas from string theory, specifically a formula called the island formula that appears to restore unitarity. But the mechanism is deeply exotic, potentially requiring that the interior of a black hole is, in some sense, part of the exterior, that the geometry of space-time near an evaporating black hole is more radically different from what classical general relativity predicts than anyone suspected. The information paradox is not yet fully resolved, and its resolution may be one of the most important discoveries in theoretical physics of the next century. One of the most important ideas in science, and one of the most underappreciated, is emergence. Emergence is the principle that systems of interacting components can exhibit behaviors and properties that are not present in the individual components and could not have been predicted from the behavior of those components alone. Water is wet. Hydrogen and oxygen are not wet. The wetness of water is an emergent property. It arises from the collective behavior of water molecules and does not exist in any individual molecule. Life is organized chemistry. No individual chemical reaction is alive. Life emerges from the coordinated interaction of many chemical reactions in a specific structural arrangement. Consciousness is organized biology. No individual neuron is conscious. Consciousness, or something correlated with it, emerges from the coordinated activity of roughly 100 billion neurons in a specific structural arrangement. What makes emergence scientifically important is that it is hierarchical and cumulative. The universe began with quantum fields. Those fields, following quantum mechanical rules, produced particles. Particles, following quantum mechanical and electromagnetic rules, assembled into atoms. Atoms, following chemical rules that are derived from but not reducible to quantum mechanics, assembled into molecules. Molecules, following biochemical rules that are derived from but not reducible to chemistry, assembled into cells. Cells, following biological rules that are derived from but not reducible to biochemistry, assembled into organisms. Organisms, following ecological and evolutionary rules, developed nervous systems. Nervous systems, through processes still not fully understood, produced consciousness. At each level, something genuinely new appears, and the new thing depends on the level below, but cannot be fully described in terms of the level below. This is what physicist Philip Anderson meant in his famous 1972 essay, when he argued that more is different. Anderson was responding to the view that all of science eventually reduces to physics, that biology is just applied chemistry, chemistry is just applied physics, and if you knew all the laws of physics and all the initial conditions, you could in principle predict everything. Anderson agreed with the first part. Everything is consistent with the laws of physics, but he argued that consistency is not the same as reducibility. Each new level of organization produces concepts and laws that did not exist at the lower level and cannot be derived from it without knowing specifically what emerged. Temperature is a concept from statistical mechanics that does not appear in Newtonian mechanics, even though temperature is ultimately the result of particles following Newtonian mechanics. Natural selection is a concept from biology that does not appear in chemistry, Even though evolution is ultimately the result of chemical processes, the universe's capacity for emergence is itself something that appears finely tuned. Most possible sets of physical laws would not produce emergence. They would produce universes where things interact, but never build toward complexity, where the energy gradients necessary to sustain organized structures are not present, where the specific chemistry that allows self-replication is impossible. Our universe produces emergence at every scale, from chemical bonds to cosmic structure, from single cells to biospheres, from individual neurons to conscious minds. The specific physics that makes this possible is the same physics that seems fine-tuned for complexity. The fine-tuning and the capacity for emergence are not independent properties of our universe. They are the same property, viewed from different angles. James Lovelock's Gaia hypothesis, proposed in the 1970s, was initially met with skepticism so intense it was dismissed by many scientists without serious engagement. The hypothesis stated that the Earth's biosphere acts as a single self-regulating system, maintaining conditions favorable to life through complex feedback loops involving biology, atmospheric chemistry, ocean chemistry, and geology. The oxygen content of the atmosphere, which has stayed within life-compatible ranges for billions of years despite enormous inputs and outputs from geological and biological processes, is one example. The mean surface temperature of the planet, which has remained in the range of liquid water despite a star that has brightened by about 30% over the Earth's lifetime, which should have caused major temperature shifts, is another. Lovelock's initial framing used intentional language that made scientists uncomfortable. He described the biosphere as wanting to maintain conditions, as if it had goals. Critics pointed out that biological systems do not have goals in any intentional sense. Natural selection produces feedback loops that happen to maintain certain conditions, not because the system is trying to maintain them, but because the feedback loops that maintain them are self-reinforcing. They persist, while less stable configurations do not. Lovelock eventually adopted more precise language, and the scientific core of the Gaia hypothesis, that the biosphere exhibits large-scale regulatory feedback, is now accepted as a productive framework for Earth system science, even if the word Gaia carries philosophical baggage. Extend this principle carefully to the universe. A universe whose laws permit stable structures permits feedback loops. Feedback loops can maintain conditions within ranges that allow the feedback loops to continue. The universe's laws do permit stable structures. They permit structures that persist for billions of years, that develop internal models of their environment, that respond to their surroundings in ways that maintain their own existence. At every scale, from cells to ecosystems to planetary systems, the universe produces systems that exhibit self-regulation. Whether the universe as a whole exhibits self-regulation at the cosmic scale is a different and much harder question. One form of cosmic self-regulation is suggested by cosmological natural selection itself. If universes reproduce and the constants are selected for black hole production, then the universe as a system has a mechanism that maintains certain properties, specifically the properties that enable black hole formation across generations. The selection pressure acts as a feedback. Universes with constants that produce many black holes leave many descendants, which inherit those constants, which produce many black holes, which leave many descendants. The feedback maintains the constants in a region of parameter space that enables complexity. This is self-regulation in a precise sense, operating on the multiverse rather than on a single universe, but self-regulation nonetheless. The question of what came before the Big Bang has haunted cosmology since the Big Bang theory was established. It is a natural question, the kind children ask and adults learn to deflect. Time, as physicists understand it, is a feature of the universe. It began with the universe, or close to the beginning, and applying the concept of before to a time before time existed is potentially meaningless. This is the standard response. It is logically coherent. It is also deeply unsatisfying. Stephen Hawking and James Hartle proposed a mathematical framework for taking the unsatisfying answer seriously and exploring its implications. They called it the no-boundary proposal, and it is a quantum cosmological description of the universe that removes the need for an initial boundary condition. In their picture, the universe is described by a quantum mechanical wave function, a quantum state that assigns probabilities to different possible histories of the universe. The wave function is defined on the space of all possible space-time geometries and matter configurations, and it obeys a quantum equation analogous to the Schrödinger equation of ordinary quantum mechanics. The key feature of the no-boundary proposal is that the wave function assigns high probability to universes that are smooth and round at their smallest time scale, universes that have no boundary, no edge, no initial singularity. Going backward in time, in a universe described by the no-boundary wave function, the time dimension becomes progressively more space-like, until at the smallest scale it is indistinguishable from a spatial dimension. There is no first moment. Time does not begin at a boundary. The universe is a closed geometry in both space and time, finite but without edge, like the surface of a sphere. Just as you can travel continuously on the surface of a sphere and never reach an edge, you can trace the universe's history backward continuously and never reach an absolute beginning. The implication is that the question, what happened before the Big Bang, is like asking, what is south of the South Pole? The question seems sensible, but refers to something that does not exist. Going further south from the South Pole does not lead to more south. It leads back toward the north. Going further back in time from the Big Bang does not lead to a prior moment. It leads to a geometry in which the concept of prior moment dissolves. The universe is self-contained. It requires no boundary condition imposed from outside. It simply is, described by its wave function, which selects for smooth, round, finite geometries. The no-boundary proposal is beautiful mathematics and philosophically profound, but it does not fully satisfy the intuition that something must explain why there is a universe rather than nothing. Hawking explicitly addressed the question of why the universe exists, arguing that a universe described by the no-boundary wave function requires no external cause. It is self-contained. But this feels, to many people, like it answers a mathematical question rather than the underlying philosophical one. Why does a universe obeying quantum mechanics exist at all? Why is there anything rather than nothing? The no-boundary proposal relocates the question rather than dissolving it. There is a simple and total fact about your situation that is easy to overlook because it is so absolute. You cannot leave the universe. There is no outside. There is no boundary you can approach, cross, or look across. The universe is not a region of space with something else beyond it. It is everything. Every direction you can point leads to more universe. Every distance you can travel, however large, leads to more universe. The universe is not a container in which you exist. The universe is the totality of existence, and you are a part of it. This has a specific consequence for the project of understanding the universe. Every tool you use to study it is built from it. Every measurement you make uses instruments made of atoms governed by the same laws you are studying. Every theory you construct is formulated in a language shaped by the evolved cognitive architecture of a primate brain that emerged from the universe's own biological history. You cannot step outside and look at the whole from a neutral position. You are embedded in the subject of your own investigation, using tools derived from that subject, constrained by limitations that the subject imposed. This is not a reason for despair. It is an observation about what science is. Science is not a view from nowhere, a God's eye perspective on a reality observed from outside. Science is the universe doing something remarkable, organizing some of its matter into configurations that can model the rest of it. When you do physics, you are a physical system building a model of the physical system that contains you. When you do cosmology, you are a part of the universe trying to understand the whole. The project is not impossible. It has succeeded beyond anything that could reasonably have been hoped for. But its character is fundamentally self-referential, and that self-referentiality has implications for what can and cannot be known. The physicist John Wheeler, one of the most creative thinkers in 20th century physics, developed the concept of the participatory universe to capture this self-referential character. Wheeler argued that observation is not merely passive recording, but active participation in constituting reality. In quantum mechanics, unobserved systems exist in superpositions. Observation collapses superpositions into definite outcomes. Wheeler extended this. The universe, before the emergence of observers, was not fully definite. The emergence of observers, entities capable of making quantum measurements, participates in crystallizing the past into its definite form. The universe brought forth observers, and observers participate in bringing forth the universe. The circle is complete. Most physicists consider this too speculative. But Wheeler's participatory universe captures something real about the structure of the situation. You are not a passive observer of the universe. You are a part of it, a product of its evolution, a configuration of its matter capable of modeling its own origins. The universe is not simply there, waiting to be observed. It has produced the observers, and in producing the observers, it has produced the only things capable of noticing that it is worth noticing. When you look at the night sky, really look at it, more than glance, you are looking at the universe looking at itself. This is not a metaphor. It is a description of what is physically happening. Your eyes are optical instruments built from atoms forged in stars. The neurons processing the visual information are chemical computers running on physics established in the first seconds after the Big Bang. The consciousness that contemplates the meaning of what you see is an emergent property of matter that has been organizing itself for 14 billion years. The sky, looking back at you through your eyes, is the universe using the most complex structures it has built to examine the structures around it. The emergence of self-modeling systems that contain representations of their own operation and use those representations to ask questions about the whole, is arguably the most significant event in the universe's history. Not the Big Bang, not the formation of the first star, not the formation of the first planet. Those were steps toward this. The universe spent 14 billion years building toward complexity, and one of the things that complexity eventually produces is the capacity to examine itself. The first time a mind asked, "Why does this exist?" the universe crossed a threshold that, as far as we know, had never been crossed before. This self-examination is more than philosophical reflection. It is productive. The last 400 years of science represent the universe understanding, with increasing precision and depth, to its own structure. We know the laws that govern matter at the subatomic scale. We know the structure of space-time. We know the history of the universe from the first fractions of a second after the Big Bang to the present. We know the process that built the atoms in our bodies. We know the scale of the cosmos, from the radius of an atomic nucleus to the radius of the observable universe, a span of roughly 62 orders of magnitude. Every one of those discoveries was the universe knowing more about itself through the specific physical process of having organized some of its matter into minds. The philosopher Blaise Pascal wrote in the 17th century that the universe's infinity terrified him. He was a man, a thinking reed, infinitely small in a vast, indifferent cosmos. But the thinking reed knew things the cosmos did not. Pascal's feeling was that consciousness is fragile and small against the scale of the physical universe. The opposite perspective is that consciousness is the universe's most remarkable achievement, that the physical universe, vast as it is, contains within it something the universe itself lacked for most of its history, the ability to understand it. You are not small in a large universe. You are the universe's most complex organization of matter, doing the thing it took 14 billion years to become capable of, knowing. Every cosmology eventually hits the same wall. Follow any chain of causes backward far enough, and you arrive at something that has no prior cause in the framework you are using. The Big Bang happened from initial conditions that are themselves unexplained. Eternal inflation operates from a prior state whose origin is unspecified. The no-boundary universe is self-contained but does not explain why a self-contained quantum universe exists. Every framework eventually bottoms out in a starting point it cannot derive from something more fundamental. This is the origin question, and it is the one question that no scientific theory has yet answered, and that may be genuinely unanswerable. The difficulty is not merely technical, it is conceptual. Every possible explanation of why the universe exists is itself a thing that exists and therefore requires explanation. If you explain the universe by saying it was created by a prior cause, the prior cause exists and requires explanation. If you explain it by saying it is mathematically necessary, the mathematical necessity is a thing that exists and requires explanation. If you say it has always existed, the eternal existence is a fact that requires explanation. Every proposed answer introduces something that requires its own explanation, regressing indefinitely. Some philosophers have argued that the question itself is malformed. The question, why is there something rather than nothing, assumes that nothingness is the default state and requires an explanation for departing from it. But nothing, in the strict philosophical sense, is not a state from which something can depart. Nothing is not a container that can be empty. The concept of nothing may simply not be coherent when applied to the most fundamental level of reality. If nothing is not a coherent concept, then why is there something rather than nothing? Is not a coherent question. It only appears to ask something profound. In reality, it is asking why the universe is not something that cannot exist, the departure from a baseline state that has no coherent description. This is philosophically sophisticated, but feels like a cheat. The sense that something needs to be explained, that the universe's existence is contingent, that things could have been otherwise, seems undeniable. Even if nothing is not coherent, the feeling that the universe did not have to exist, that its existence is a contingent fact rather than a necessary one, seems genuine. Cosmological natural selection addresses this feeling by embedding our universe in a larger structure with its own history, but the larger structure also requires explanation. Loop quantum cosmology's bounce universe had a prior contracting universe, which also requires explanation. The regress always continues. The most honest statement that can be made is, we do not know why the universe exists. This is not a temporary gap waiting to be filled by the next calculation. It is a structural limit on explanation that may be fundamental. Every framework we have for explaining things assumes some background context, some prior state, some set of laws, some space of possibilities within which things happen. The question of why there is any background context at all, why there are any laws, why there is any space of possibilities, this question has no framework within which to answer it. It is the question at the absolute bottom of inquiry, where the chain of explanation ends not in an answer, but in the recognition that there is nothing further to appeal to. Consider what we have established across this entire investigation. The universe runs on physical constants that appear calibrated for complexity. The calibration cannot be derived from any deeper theory. Several serious explanations have been proposed. Deeper physical law making the constants necessary, selection through reproduction of universes via black holes, selection through anthropic observation in an enormous ensemble. None is proven. All are in active scientific discussion. The constants are what they are, and their specific values are connected. The same values that allow stars also allow chemistry, also allow planets, also allow life. The network of constraints is simultaneously satisfied in a way that permits everything interesting to happen, and the probability of this occurring by chance is, to any honest assessment, essentially zero. The universe has a life cycle. It began in a hot, dense, extremely ordered state. It expanded and cooled. The first structures formed. The first stars burned and died, seeding the cosmos with heavy elements. Subsequent generations of stars built on this chemical legacy, producing increasingly complex molecular environments. Planets formed around stable stars and provided surfaces where chemistry could proceed in liquid water over geological timescales. Eventually, self-replicating chemistry appeared. Life evolved. Nervous systems developed. Minds emerged. The universe became, in some of its regions, self-aware. The cosmic web, the large-scale structure of the universe, organizes itself according to the same network principles that organize neural tissue. The same mathematical rules of network formation appear across scales from neurons to galaxy clusters. The fine-tuning that makes stars possible also makes chemistry possible, also makes minds possible. The constants are not separately tuned for physics and separately tuned for biology. They form a unified set of values that enables the whole cascade of emergence from hydrogen to consciousness. Dark matter provides the scaffolding from which all structure forms. Dark energy drives the expansion that determines the universe's long-term fate. Both are unknown in their fundamental nature. The dominant ingredients of the universe, the things that determine its large-scale structure and its future, are mysteries. What we do know, the 5% that is ordinary matter, the atoms and chemistry and stars, has been sufficient to produce us. The 95% we do not understand is the context in which we exist, shaping the universe we inhabit without our being able to identify it. What converges from all of these threads is a picture of a universe that is, at minimum, extraordinarily well suited for the emergence of complexity. Whether this suitability is the result of natural selection acting on a population of reproducing universes, or of anthropic selection within a landscape of possibilities, or of some deeper physical necessity not yet identified, is unknown. But the suitability itself is not in question. The universe does not merely permit complexity, it generates it at every scale over the entire span of its history, and it has done so in a way that produced the specific complexity of minds capable of noticing. Everything you know was built by this universe from itself. The atoms in your brain were assembled in stellar cores that died before the solar system formed. The chemical processes that constitute your thoughts run on physics, established in the first seconds after the Big Bang. The specific constants that allow your body to hold together and your neurons to function were either chosen, selected, or mathematically necessary by mechanisms we do not understand. The consciousness that allows you to ask whether any of this means anything is an emergent property of matter that has been organizing itself for 14 billion years under laws that appear calibrated for exactly this kind of outcome. You are not in the universe. You are the universe, in the specific configuration that thinks about itself. The question of whether the universe is alive is not a question you are asking from outside. It is the universe asking from inside, using the only instruments it has for asking questions, the minds it evolved. The recursion is real. The question and the questioner are the same object. And what the questioner has found, after careful examination, is that the universe has properties, fine-tuning, self-organization across all scales, the emergence of complexity, the production of self-aware minds, that are consistent with something more than a mindless accident, but less than anything we have a word for. Not life in the biological sense, not consciousness in the human sense. Something for which our conceptual vocabulary is still insufficient. The science does not say the universe is alive. The science says the universe has properties that, when examined carefully, raise the question of whether alive is too small a concept. The constants are set at values that permit the emergence of complexity by mechanisms that remain genuinely mysterious. The structure of the cosmos, from quantum entanglement to cosmic web, exhibits the same organizational principles at every scale. The universe began in an extraordinarily ordered state and has been running through that order ever since, producing in the process an unprecedented diversity of structures, including structures capable of asking why. These facts do not add up to consciousness. They add up to something that science is still in the process of characterizing. You are trapped inside this thing. You cannot leave. You cannot observe it from outside. Every thought you have about it is a physical process occurring within it. The imprisonment is absolute, but it is not a prison. It is a membership. You are not trapped in the universe. You are part of it, one of its most recent and most extraordinary configurations of matter, equipped by billions of years of cosmic and biological evolution to understand something about the whole. The universe has been around for nearly 14 billion years and has produced, in that time, everything from quantum fields to consciousness. It will continue for timescales so enormous they make the current age look like a single moment. What it will produce in those vast future eons is unknown. What it has produced so far, you, and the capacity to ask the question you are now asking, is the most remarkable thing in the observable universe. And nobody told you that the thing you live inside, the thing you are made of, the thing you are a part of, might be doing something that resembles what living things do, might have been doing it since before any star ever burned, might be doing it still, in ways so large and so slow that the only instrument sensitive enough to detect it is exactly the kind of mind that a universe full of stars and heavy elements eventually builds. The question is real. The investigation has just begun. The answer, whatever it is the most important one anyone has ever looked for.